Lesson 64, derivatives of inverse trig functions / what to memorize. So this is the lesson where I introduce derivatives of inverse trig functions. Now, when I introduce these, we're going to kind of go through how you can develop them, how you can find them, because that is a good skill to have. On the flip side of it, we're going to talk about, if I recall, I think it's sine and tangent are the two that come up the most that you really need to know. Cosine as well. The others like cotangent, secant, and cosecant don't really come up. They don't fall into that memorization category as much, but sine inverse and tangent inverse do. Cosine is a lot like sine, of course, so that makes it easy to know. Okay, so as we look at these derivatives of inverse functions, so what D is saying here is this is saying the derivative of sine inverse of x over a, where a is some constant. Okay, a represents a number. That could be a 1 if it's just sine inverse of x, or obviously there could be a number there. And this is saying that the derivative of sine inverse of x over a, and on top it says dx, so just think of that as a 1 over the square root of a squared minus x squared. Okay? With the derivative of cosine inverse of x over a, the only difference is it's a negative 1 on top over square root of a squared minus x squared. With derivative of tangent inverse of x over a, notice there's an a here. So whatever your a value is over a squared plus x squared, there's no square root sign over there. As you look down below, that next row, they get a little bit different, of course. Cotangent inverse is negative a over square root of a squared plus x squared, so you've got the negative. Secant inverse, a over x square root of x squared minus a squared, and cosecant, negative a over x square root of x squared minus a squared. So you definitely see the positive negative connection and all of that. Now, let's practice with example 1 here. And example 1, let y equals arc sine of x over a, find y prime. So again, this is kind of the, not using the formula up there, but the whole idea of developing it. Now, arc sine is another way for saying sine inverse, right? So this could also be written as sine inverse of x over a. Okay, that's just general calc knowledge we need to know, right? Arc sine, sine inverse, interchangeable. Based on the fact, other than it's listed up at top, but if we're just trying to find this here without using our definition, well, if I don't know how to do a sine inverse, the derivative, how do I get it out of this sine inverse form? Is that quite? Okay, so the idea here of an inverse, you're switching x and y, generally speaking. And with sine inverse, you're switching like your input and your output type thing. So it's the idea that if we're doing the sine inverse says the sine, how do I want to say this? Normally with sine, we say the sine of this angle is equal to what number, right? The sine of an angle is equal to a number. Sine inverse is saying the sine inverse of this number is equal to an angle. So you're switching those pieces. So the idea that when we switch, it's not switching x and y exactly, but it's switching your input and output. So the sine of y is equal to x over a. And That's the idea. The idea that sine of 30 degrees equals 1/2. Sine inverse of 1/2 equals 30 degrees. It goes back to that definition, right? If I'm not being very clear, which I kind of feel like I'm not being as clear as I need to be. Now, as we look at this, okay, I'm debating which order I want to do this in. Let's go ahead and talk about, if we want, we're trying to find y prime. So let's go ahead and talk about differentiating this. Notice we've got y and x, so we're going to have to use our differentials of x and y in here. What is the derivative of sine of y? Okay, so the derivative of sine of something is cosine of something. So derivative of sine of y is cosine y, and then we're going to say times dy, because again, we've got y's and x's in here. What about the derivative of x over a? 1 over a, because a is a constant, right? So when we talk about x over a, that's the same as saying that is 1 over a times x. Does that equivalency help there? And so what's the derivative of 1 over a times x? That constant of 1 over a times dx. Now, if we're trying to find y prime, then what's another name for y prime when we're working with our differentials? Yeah. Trying to find dy dx. Can you take your current equation and solve it for dy dx? Yeah, I already have my dy on the left. I'm going to divide the dx over to join it, yes. And then what do I need to get away from dy? Cosine y. So we're going to divide the cosine y into the denominator of the other side. So what I'm going to write, I still have dy. I'm going to divide both sides by dx. So that puts my dx in the denominator of the left side. On the right, I still have 1 over a, and I'm going to divide by cosine y, which I'm going to write as 1 over cosine y. Okay. Now, so the derivative right now, 1 over a, okay, that's fine. 1 over cosine y. That can't really be in our answer. Because if we're trying to find the derivative of y, we can't really have a y in there. Okay? So, this is where we're going to go back to this relationship right here. I'm not writing for some reason. Okay. We're going to go back to this relationship right there. Sine of y equals x over a. If we talk about sine of y equals x over a, can you set up a triangle that shows that relationship? Think right triangle here, yes? That's a horribly drawn right triangle, but you get the idea. Sine of y equals x over a. Okay, so sine of y, that means y is an angle, correct? And I just chose to make y that bottom left angle. Sine of y is x over a. Opposite over hypotenuse. So the opposite side is x. The hypotenuse is a. So that's the connection we have there. Now, we need to know, to fill in down here, cosine of y. Cosine of y is going to be adjacent over hypotenuse. But we don't currently have an adjacent side. How do I find the length of the adjacent side? Based on the fact that the other two sides of this right triangle are a and x. Pythagorean theorem, right? Because we need to know what that side is in order to do our cosine. So, Pythagorean theorem, for lack of a better, I'm going to call this side b for the moment. And our Pythagorean theorem would say b squared plus x squared is going to be equal to hypotenuse squared of a squared. Can you solve that for b? B squared is a squared minus x squared. And the square root of b is going to be square root of a squared minus x squared. And what is that? Our missing side down here. That is the square root of a squared minus x squared, which again, as I said earlier, is necessary to find the cosine of y. It's all skills you know, right? I'm just trying to make you pull them all together. Okay. So going back over here, dy dx was equal to 1 over a times 1 over cosine of y. Go back to your triangle. What is the cosine of y in regards to my triangle over there? Square root of a squared minus x squared over a. Right? Based on the work I already did over here with Pythagorean theorem, cosine is adjacent over hypotenuse. So square root of a squared minus x squared over a. Now at this point, it's just a matter of doing some cleanup, would be my thought. So dy dx is 1 over a times, what about 1 divided by this fraction? Yeah, multiply by the reciprocal, and it's 1 times a over the square root of a squared minus x squared, so really this just becomes a over the square root of a squared minus x squared. And guess what happens? Your a's cancel. And once the a's cancel and we put this together, dy dx is 1 over the square root of a squared minus x squared. And what is that the derivative of? That is the derivative of arc sine or sine inverse. Does that match with what's up in the chart? It does. The dx is just in a different form in that case, right? But if you move that dx off to the side, you've got 1 over the square root of a squared minus x squared. Now, obviously, probably just easier to memorize it, isn't it? Okay? Rather than to have to try and do all this work. But here's the connection of where it comes from. Okay? I'm trying to think, which ones are we working out today? Okay, so we're set to work out sine, cosine, tangent, and cosecant. What are you feeling? Do you want to work cosine out? I will say, I guess working cosine out will help kind of maybe clarify what we just did here. Is this a jumble what we just did here, or did you follow okay?
I want to find one more.
Huh?
I want to find one more person.
Okay. And I'll probably definitely work out tangent because it is a little bit different, but okay. So cosine. Y equals arc cosine of x over a. Find y prime. I'm going to use the same techniques I just did. Okay, this one's going to kind of definitely follow what you just saw. So first of all, another way to write arc cosine. Y equals cosine inverse of x over a. How do you switch from cosine inverse to cosine? Switch your inputs and outputs. So cosine of y equals x over a. It's easier when I don't have to explain it this time around. Now we're going to take the derivative of both sides. Derivative of cosine of something. Negative sine of something, so negative sine of y times the derivative of y, which I'm going to call dy, because I'm working with y's and x's. Okay? The derivative of x over a. That really has the x has a coefficient of 1 over a, so the derivative of 1 over a times x is 1 over a dx. Can you solve this for dy dx? If I solve this for dy dx, I've already got dy on the left. I want my dx on bottom, so I'm going to divide it to the other side. I already have 1 over a on the right. And then I'm going to divide over negative sine y. So I'm going to write it as 1 over negative sine y. Stop me if you don't like what I'm doing or if something's not quite as easy to follow this time. Or if you still need the explanation, I didn't give it. Okay. What's the catch I need to know here? I need to know sine of y, don't I? Which means I need a triangle based on this information right here, based on cosine of y. I just totally drew that triangle the other way. How confusing am I going to make this? Can we handle this? I mean, all it comes down to is where are you putting, it's cosine of y, so what angle are you making y? Probably should not have switched that triangle, but I did it without even thinking. I'm going to challenge you guys today. I know you guys are thinking you don't really need to challenge me like that, but okay, so cosine of y, there's y, is x over a. So what's x? X is adjacent. Hypotenuse is a. What is that other side? Can we use our information from last triangle? The last one, we had a hypotenuse of A and a side of X. Isn't that what I have again this time?
Yep.
It's just a different side, but your sides can, you know, they could interchange, right? So what's my other side going to be? Correct. Square root of A squared minus X squared. And if you don't believe me, do your Pythagorean theorem work, right? Okay, so let's fill this in. dy dx is 1 over a times 1 over negative of sine y. So what is the sine of y here? Opposite over hypotenuse. So square root of negative of square root of a squared minus x squared over a. And you maybe see where this is going. dy dx. Still going to leave it as 1 over a. 1 divided by that fraction is 1 multiplied by the reciprocal. This can be negative a over square root of a squared minus x squared. The a's will cancel. And dy dx is negative 1 over square root of a squared minus x squared. Okay. Was that one a little easier to follow this time? Since you'd seen the steps, it was a little easier the second time through? Okay. There's part of me that wants to skip tangent. There's part of me that sees like tangent as an important one. So I think we're going to go ahead and do tangent. I'll definitely skip the one at the top of the back side. Still going to be the same process, right? This is y equals tan inverse of x over a. We don't know the derivative of tan inverse, so we're going to switch this to tangent. You switch from the inverse to the regular function, my input and output will switch. So tangent of y equals x over a. Okay, this might be a challenge for a moment. When we take the derivative here, what is the derivative of tangent of something? Yep, secant squared. Derivative of tangent of something is secant squared of something times the derivative of something. So derivative of y, dy. Derivative of x over a for the third time in a row, 1 over a times dx. Solve for dy dx. Keeping my dy where it is, dividing over the dx. If you don't see this, then put in that you're dividing both sides by dx. And I'm also going to, see, I'm going to keep the 1 over a, and I'm dividing by secant squared y. Now, You can leave it as 1 over secant squared y if you prefer. But what is 1 over secant equivalent to? What'd you say? Cosine. Cosine and secant are reciprocals, yes? I don't know about you guys, but I'm much more comfortable working with cosine than I am secant. I just have to think harder for secant. I can do it, but I have to think harder. I don't want to have to think harder. So you could rewrite this dy dx 1 over a, and then 1 over secant is actually cosine. So 1 over secant squared is cosine squared y. So I now have 1 over a times cosine squared y. The key is I need to know what cosine of y is. So guess what we have to do? Triangle again. This time, our connection we are given is the tangent connection. So the tangent of angle y, so write in a y for one of your angles. Tangent of y is x over a. What's our tangent saying? Opposite over adjacent. So opposite my y is x, adjacent is a. So my legs are x and a. Can you find the hypotenuse? It's the square root of a squared plus x squared. Pythagorean theorem, I just didn't work it out. So, dy dx is 1 over a times cosine squared of y. What is cosine of y? Cosine being adjacent over hypotenuse. So a over square root of a squared plus x squared. Though since it was cosine squared, we're going to square that fraction. What do you see? One of the a's cancel, so I'm going to have a left on top. And what happens when you square that square root? You just get what under the square root, what is under the square root, which is a squared plus x squared. So does that match with what's up top? The derivative of tangent inverse? Up top it says a dx over a squared plus x squared. Okay? Okay. The one at the top of the back, I'm not going to take the time to do. I'll be honest. I rarely, if ever, see anything about secant and cosecant inverses. I rarely see them. So I'm not, I will say if you work this out, you're going to end up with dy dx equals negative a over x times the square root of x squared minus a squared. Give you guys a time, you can probably work that out on your own. It's probably doable for you. Okay. It's a little bit about where they come from, how we can find them. The connections there. So the second half of this, the ones you definitely need to know are sine and tangent. You need to be able to recognize them because they pop up, okay? So you'll realize real quick that you need to recognize them. So the idea here, the derivative of sine inverse of x over a, keep in mind, think of that as a 1 over square root of a squared minus x squared. Over here, the derivative of tangent inverse of x over a, notice, and I don't know, maybe it's a over a squared plus x squared. Whereas this one is 1 over square root of a squared minus x squared. And keep in mind, where do those a's come from? The fact that it is sine of x over a and sine inverse of x over a and tangent inverse of x over a. So just kind of realize those connections. Okay, let's look at example 5 here. Now we're using these rules. If y is tangent inverse of cosine x, we're going to get fancy right off the bat. What is dy dx? So what is the derivative? Okay, there's my start. Dy dx equals. Now, tangent inverse. What is our tangent inverse rule? Because tangent inverse is our function, right? Our tangent inverse rule is a over a squared plus x squared, which means we need to define what's in the a position, what's in the x position, right? And so one of the first things I will always encourage you to do is this inside right here. This cosine x is in the position of what? It's in the position of x over a, right? So if you make cosine x a fraction, it is cosine x over 1. And so what I'm saying here is that x over a is equivalent to cosine x over 1. So in the position of x, sometimes it's a 2x or an x squared or whatever. Well, we're getting fancy. In the position of x is cosine x. The denominator, in other words, if there is no denominator, obviously we know it's 1. So in the position of a is 1. So when we fill in that formula, every place I see x, I have to think cosine x. Every time I think a, I have to think 1. Okay? So let me go back here. What is the derivative of tangent inverse of something? Derivative of tangent inverse of something is a over a squared plus x squared. So what am I putting in position of a? What did we say a was? 1. Because that's my a, over a squared plus x squared. What is a squared? 1 squared. Plus, what is in the position of x? The position of x is cosine x. So since it was a squared plus x squared, I'm going to say 1 squared plus cosine x squared. Why did I write it like that? Oh well, I did. That's why. I just did. Now, okay. What?
That's like a triangle.
Now, let me think about this original question one more time, so we've got to think about one more detail. The question was, what is the derivative of tangent inverse of something? And the derivative tangent inverse of something is this rule, a over a squared plus x squared, times the derivative of something. As in, do you see what I'm saying here? We have to consider a chain rule. Because our inside is not just a plain old x. So when I say what is the derivative tangent inverse of something, it's this, the fraction, times the derivative of something. What is the derivative of something? So what's the derivative of cosine x? Negative sine x.
So why didn't we do chain rule before?
Before when?
As in, like,
On the front side, it was always just an x or a y that we were taking the derivative of. And we did do a chain rule in that we did the dy and the dx piece, but it was never anything more. The insides or the something was never anything more than an x or a y. And when you have the chain rule of the derivative of x or y, it's just 1. Now, to clean this up, here, I was going to write a comment that this negative sine x came from a chain rule. Just as a reminder. To clean this up, there's not really anything we can really do with this. So I'm going to say dy dx. I will say this negative sine x can be multiplied and put in the numerator. So I'm going to say negative sine x over 1 squared is 1 plus, and I'm going to write this as I should have to begin with, cosine squared x. And since I don't have anything else I can do with that, so I'm going to leave it as is. That was probably the more difficult one to get us started with. Well, I don't know. These all have tricks today. It's just one of those things. They have tricks. Do you have what you need? Okay. So I'm going to move to example 6 if you guys are ready. Y equals arc sine of 2x. Find y prime. Arc sine is the same as saying what? Sine inverse. So this really says y equals sine inverse of 2x. Now if you want to go ahead and think about the form x over a. Okay, like I did up above earlier. X over a, what's in place of x over a? It's just the 2x, right? What's 2x as a fraction? 2x over 1. So when we think about x over a, you're thinking about 2x over 1 again. I shouldn't say again, but so when in the x position, we're going to be putting in 2 x's. In the a positions, it's going to be 1's again. Okay, you ready to use your rule up above? We're being asked to find y prime. The derivative of sine inverse of something. If you look up top, it says derivative of sine inverse of x over a, so derivative of sine inverse of 2x over 1. On top of the fraction is going to be a 1, right? Because there's just 1 dx up there, over the square root of a squared minus x squared. What am I putting in for a? 1. So that's going to be 1 squared minus x squared. What am I putting in for x squared? So it's going to be 2x quantity squared, if you will. Now, same question I had to ask on the last problem. Overall, my question is, what is the derivative of sine inverse of something? So the derivative of sine inverse of something is this fraction times the derivative of something. And the derivative of 2x is 2. So again, that is our chain rule piece. I'm going to put this over here. Okay, clean it up. That 2 can multiply and go on top. 1 times 2 is 2. Under your square root, do some cleanup. 1 squared is 1 minus 2x quantity squared is going to be 4x squared. And that would be how you'd likely read it. Excuse me. Now, the next one may look like it doesn't belong. But trust me, it does. We're doing all these derivatives today, and then they throw in integrate. As I said, it seems like it doesn't belong, but guess what? It does. This is one of the tricks to working with inverse derivatives, is you have to work to recognize this. This is an integral of one of these we've done today. In other words, this is going backwards on one of the ones we've done today. What does that look kind of like the derivative of? Can you see the connection to tangent? I'm going to side note because I don't have it over there to point, but if you look up top, no, okay, writing too small, or not writing the way I want that. The derivative of tangent inverse of x over a is a times dx over a squared plus x squared. Can you see how that connects? That's a connection you have to learn to make. Okay, when you go to integrate 1 over 1 plus x squared, you'll very quickly figure out, I don't know how to integrate that stuff. Okay, and that's where you have to start searching your, brain for, okay, what is that similar to? So yes, we want to think tan inverse x. And I guess I could have just written it over here. The derivative of tan inverse of x. So if we're just looking at plain old tan inverse of x, that would be x over what? X over 1, right? And the derivative of tan inverse of x over a is a. Well, what would be my a value? 1 over a squared. So that's going to be 1 squared plus x squared. And what is my x value? It is actually just x this time. So the original problem was the integral of 1 over 1 plus x squared dx. What am I going to write my answer as? Tan inverse x
Or no, let's see.
we're integrating, and it's an indefinite integral, so plus c. And to be honest with you guys, does that one require any work whatsoever? No, it doesn't. I'm just trying to help you catch the connection.
Thank you.
Okay? Once you see that connection, there is no work to show there. It's just one to recognize. I just couldn't expect you to recognize it right now. Okay? Do I have time? Okay. We're going to try it. I don't know if I have time. That's your lesson 64, right? You know what you need to do in relation to that. Somewhere here, I have pulled up yesterday's last example. Let's go back. We'll see what we can do with this one. Okay. Can you change your brain out for me real quick and backtrack to yesterday? I know, it's a lot, right? Like, oh, we were on one train thought, now we got to do this other one. Okay, going back to yesterday. The whole idea of maximum minimums, thinking about critical points that they can be when the derivative equals 0. They can also be endpoints. They can also be when the derivative does not exist. Notice it states a function f is continuous. We can't talk about this if it's not continuous. On the closed interval, -2 to 4. Also, f of -2 equals 2, f of -1 is 1, and f of 4 is 5. Furthermore, the function f prime and f double prime have the properties indicated in the table below. Okay. Information galore. Now, just realized it doesn't say what you're supposed to do. So the question we are ultimately going to be answering is we are going to be finding the values of x for which f attains max and min values. So our goal is to find the values of x for which f attains max and min values. I'm going to end up sketching a graph is what I'm going to end up doing. Okay, to put all this information together. Now we're specifically talking on the interval from -2 to 4, correct? Information they share with us. They tell us that f of -2 equals 2. That is the ordered pair -2, 2, correct? When they say f of -2 equals 2, that is the ordered pair of 2. And so can I go ahead and graph that point? I can. They also continue to tell me f of -1 is equal to -1. So that is the ordered pair. -1, -1. So I can graph that point, correct? We're going to play connect the dots. And then they told me f of 4 is equal to 5. If f of 4 is 5, that is the ordered pair 4, 5. That's just, we haven't even gotten to the chart, guys. Sorry. Okay. From -2, that's not supposed to be say -2. -2 does not make sense. From -2 to -1 is what that's supposed to say, sorry. The first derivative is negative. What does the first derivative tell me? First derivative tells me if we are increasing or decreasing. So a negative derivative means that we are decreasing. What does a negative second derivative tell me? concavity. So between -2 and -1, we are decreasing and concave down. So if I kind of tell you real quick, kind of like that. I know, I have to be extra quick. Now, an undefined first and second derivative means at -1, this is a hard point. You might call it a cusp in some situations. It's not going to be a rounded point. It's going to be a hard point. So it's going to be a point. Okay. -1 to 2. Positive first derivative means we're going to be increasing. Negative second derivative means concavity, concave down. So to go from this point at 1 to the point at 2, it's increasing but concave down. Oh, to 2. Oops. Oh no. Okay. Now, real quick, right here, the 0 is a critical point. The second derivative is also a 0. This ends up being an inflection point. And so what's happening above 2 is my concavity is going to change. Because from 2 to 4, increasing derivative, concave up. So we're going to, the first part from -1 to 2, I'm going to increase and be concave down. Then above 2, I'm still increasing, but I'm going to kind of switch and be concave up. We don't know where above 2, just whenever it hits 2. So that's kind of my graph. It is, but now we just wanted max and min values. When does the min happen? When x equals -1. When does the max happen? Above x equals 4. That was quick. This is on video if you need to go back and look at it later because it was quick, I know. But I think I got everything to at least somewhat flow.
Yeah.
Okay.
I had a good time.
Okay. It was probably actually better than yesterday's lesson. I apologize to those of you sitting here in class that I have held you over. It has, we're at least caught up on lessons. So
That's okay.
I love your class. We'll be over anytime.
I know, but now it's the